Good evening, everyone. Happy equinox, or recent equinox. It is, in fact, our March Speakers Night for 2023. Welcome to RASC Toronto Centre. We are, in fact, online tonight, and I am Dr. Elena Hyde, the second Vice President of the RASC Toronto Centre. And this is our Speakers Night presentation. So, hooray, you're in the right place. This is one of two types of gatherings that we have online these days, not at the Ontario Science Centre due to the ongoing pandemic. But later on tonight, we'll have a little bit of more chats about our various programs from our president, Tom Luton. However, before we get going on that, we have a special event to kick off. We have, in fact, our March speaker. So I'm going to do a short little introduction, which is probably not going to do our speaker complete justice. But tonight we are lucky enough to have Parisa Nozari, a master's candidate from Queen's University. She's actually starting her PhD journey later on this September, I believe. So, wishing her lots of luck in that. And she has been studying all kinds of interesting things that I believe she'll tell us a little bit more about tonight, looking at the evolution of dust grains and their properties to contribute into things like star formation and awesome stuff like that. In particular, looking at the Orion molecular cloud, which is, I know, a favorite of some of our observational astronomers to gaze at, should I say. So beyond doing research, she's also been a representative for the physics graduate students on committees and the Casca GSC. And you might actually recognize her name. She was, in fact, our 2022 July 18th to 31st astronomer in residence for York University and the Killarney Provincial Park, a program near and dear to my own heart, if you if you remember. She did some wonderful astrophotography while she was up there, and I believe she will be telling us maybe a little bit about that as well. Looking at, of course, all kinds of wonderful things, from how to do imaging, maybe even a little bit of solar. I'm not sure. But if you want to find out about her full experience from York University and the astronomer in residence, it is actually on yorku.ca/science/observatory/blog, Parisa Nozari. So you can find out all kinds of great things about her, and she's actually here to tell us even more great things. So without any further ado, Parisa, please take it and us up, up, and away.
Hi, everybody. Thank you, Elena, for such a nice introduction. I'm so happy to here with you, and thank you for inviting me. So tonight I'm gonna talk about all the cool things about dust grains and how they actually contribute to the star formation process, which is one of the most fundamental process in the universe. And also the second half of my talk gonna be a little bit just very easy tips for anybody who has a digital camera and are interested in be amazed and enjoy the beauty of the nature. So you can just pick up a dark spot, dark sky spot, and then go and then put those general very very easy tips you can just go and enjoy with your camera. So let's dive in. So first of all, I want to start actually with the star formation process, because the star formation process is one of the most fundamental process in the universe. And because all of the galaxies that you see, all those clusters are actually made out of stars. So understanding how these objects actually form is quite important, and it's a little bit it's not a little bit a very complicated process, because so many physics at so many scales, different scales happening. So for understanding this very fundamental process, we have to know a lot of physics on different scales. Because although it is very one of the most fundamental, our understanding is a very very still limited, and it's poorly understand yet, because in the past we didn't have actually the opportunity to detect what it's beyond the star formation, which I'm gonna like talk about it a little bit more and later on in the slides. And but like nowadays with so many cool instruments like JWC that you all might heard of it nowadays, we have the opportunity to actually capture and detect all those like structures that an environment that stars actually form within. So it's a great opportunity to dive into that field of study. So I want to start with this question that what is actually space made of? And you might be wonder that space is actually not that, although like you see like full like so many stars, millions of million stars and galaxies, the space is actually very empty, but empty out of baryonic invisible matters. What does actually mean? It means that for example, if we have like the whole universe, only 5% of like the whole universe is made of the visible matter, which means all of the cool stuff that you see, like the stars and galaxy, only consist of 5% of the whole universe. And the other 95% are made of something we call it dark energy and dark matter. And nobody actually still know what are they made of, but they're there and we know like they exist because the physics work in this way under the condition of their existence. So you might be interested that while you look at the sky, go to the stargazing and you see a sky full of like the stars, they're only 5% of the whole universe. So, and out of this 5%, we have so many things like galaxies, stars, and but like the only 15% of that 5% is something that we call interstellar medium, which means between like the two stars, or like between like the environment of the galaxy, there's a region of which we call it the nursery of the star formation. And out of like these 50% of the interstellar medium, only less than 1%, or approximately around 1%, made of dust grains. So what does that mean? Actually, this type of dust grains, which we call them space dust, it's so much different of with what we know as like the dust on Earth, because the dust on Earth can be very gross. It can be like hair, plastics, like so many things. But the dust in the space is actually different, which I'm gonna like talk about it a little bit more. And the other 90% of the interstellar medium are in the gas phase, which means like the other molecule and like the atoms that are like in the form of the gas. But these dust grains are different because they're actually a solid grains and made of generally there are different type of like dust grains in the space, but generally we categorize them into two groups. One like the carbon rich dust grains, and the other one is silica dust grains. And the silica dust grains is what we actually recognize as a sand on Earth. So what is like their size? All the dust grains that we are talking about it in the interstellar medium are in the scale of the micrometer. So they're very, very teeny tiny, but they're complicated in their composition, which means they're not like a simple atom or molecules. They're actually a combination of like more complex structure and composition. And so that's, but they're actually a solid grain that we know them as dust. And they're so important in understanding the formation of the stars because they create the environment for the stars to be born, and also create a very, very significant role in the galaxy evolution, because once we have the star, then the stars cluster together and then form like a bigger structure named galaxy. So, but like the question is that how we can detect these dust, because for example, let's assume that we're you and because these type of like the solid grains do not emit photons necessarily or light, and our optical telescopes are not sensitive to capture to detect them based on just be sensitive to the lights or the photon. For example, like let's assume you with a bunch of like your friends sitting in a very, very dark room. So if I just like put my phone, like my smartphone, and just like try to take a picture, I capture nothing. But for example, if I have the infrared camera, which is sensitive to the heat, I will be able to detect all, like every single individual which is sitting in that room. It is kind of like the same story for the dust as well, because they're kind of like, as soon as like there emits the heat and the specific temperature, let's say around like 8 to 100 Kelvin, so approximately around minus 250 Celsius, at that temperature dust actually emits the heat. So if we have the instrument which is sensitive to the infrared or millimeter, millimeter, like the range of the wavelength, we can detect the dust. So that's what actually happened. And very a great example is the Bernard 68. It's a molecule cloud sitting in our galaxy, and for such a long time, people were questioning that what is this empty area in that space? That was such a like a big question back in time. And then they figure out it's not actually empty. This is the region of molecule cloud, very rich in dust, and it's thick enough that could actually block all the lights block the lights behind that cloud. So for example, you see at the left that if I have the source and if I have like the matter, for example, let's assume here it's the molecule cloud, very rich in dust and actually thick. So it doesn't allow the light of my source to pass through this matter, and it doesn't allow my detector to detect that. So as I mentioned, we need an instrument which is be sensitive to another properties, which is heat right now. So these kind of like this Bernard 68 molecule cloud, it's very interesting because people like the later in time figure out it actually blocks around 3,700 back like stars, Milky Way stars at its background. So which was like one of the like the initial question that people asked was just like by seeing Bernard 68. So, and then the question is that, for example, here we have a great example of like the comparison between Hubble versus James Webb telescope. So Hubble is operated actually in visible lights, which means are mostly sensitive to the object, the celestial object like stars that emit lights. And we can capture them. And then you see like huge difference between what JWST actually captured in the sky, because this is an instrument which is sensitive in the infrared, in infrared wavelength, so which means allows us to detect us as they emit heats, and that in those kind of like the range of the temperature and wavelength. So this is very interesting. So the last image was like actually like the star formation nursery. So these are like a huge molecule clouds, but like to give you a little bit like sense that how big are they. So if you have like a cloud, which let's assume like it's around like more than 10, it can be more than 10 parsecs. So how big the parsec is? Parsec is around 3.4 light years. And most of you may like already heard about this analogy and example, that if, for example, I am sitting in a spaceship and travel with the speed of light, it actually take me 3.4, 3.5 years to travel with a distance of 1 parsec. So let's assume how 10 parsec, how big can a 10 parsec can be. So and within those like the molecule cloud, those region which are like more dense, which like they gonna be they're gonna be like be like in a subgroup of clumps and then filamentary structure. And within that filament, which we have like a very dense region out of dust and gas, then all of them can coagulate to each other, meet each other, get gathered together and collapse under the gravity. And then we have cores. And to understand how big a core can be, it's point zero point point 0.05 to 0.1 parsec, which means approximately 10 to a scale of the 10 to 4 times of the distance between Earth to Sun. So if you imagine all those micro meter size of the dust grains need 10 to 4 times of the distance between Earth to Sun to gather together, they need such a huge amount of space to gather together and collapse under the gravity to form the stars, which is like a huge amount of the space, which I'm always like making good jokes about it, because in astronomy these kind of scale are counted as a small scale, but it's I just wanted to give you some sense that how big that small scale in astronomy is, because when people talk about galaxies, they talk about like 100 parsecs, which are, so if you imagine how big one parsec can be, then you feel that it's insane. So then another question is that, okay, we know what dust is made from, like what is like the approximate size in the interstellar medium. They have to come together, coagulate, and collapse under the gravity. And another question is like, okay, but we need a condition, for a specific condition in the environment of the interstellar medium for the stars to form. What are those conditions? So here, if these are like a map of the one Milky cloud in a torus, which taken by Herschel. So it has like a mass around 10 to 4 times of the mass of the sun. So the one of the two most fundamental environments, or actually condition for those environment for the stars to form, is these region needs to be dense and cold, because while like the environment is so active, so many things happening, and it heated up, at those kind of molecules they're all just like jumping from region to region, so they do not have enough time to come together and collapse under the gravity. So we need to cool down the whole environment for the stars to form. So how it happens? So here dust comes in. So dust actually has three main roles. Dust also can heat up the environment, like the interstellar medium. But let's figure out how they heat and cool down the environment. So first of all, here is like if you imagine like this is the dust grains, like their molecules all like they form more complicated compositions, and they come together and they create that solid grains. This solid grains, when actually a photon from another star or from another environment comes, their little skeleton starts to vibrate. And once they vibrate, they emit another photon. And like these processes happen and happen over and over again. But if there's like an ultraviolet photon comes from the stars, it has enough energy to trigger like the dust grains and emit the electron. And so we need more high energy photons like ultraviolet. It can kick out the electron. And once the electron is kicked out from this dust grains, goes and heat up the whole interstellar, like that region of interstellar medium. So imagine we have so many solid grains, a solid, and all of those, a part of it actually try to heat up the interstellar medium. But the other on the other hand of like the story, dust also cool down the environment. How? So here how it works. So if like we have like a more bigger like dust grains, so they actually like, let's imagine that like a part of like the interstellar medium in a molecule cloud, it's cool enough, and like all those kind of hydrogen molecules created already, and like the environment is ideal. But these dust grains actually come and shield up all those environments from and prevent the ultraviolet photons coming from another stars to pass through into that region. Because without dust, if we do not have the dust, those ultraviolet lights come and break down all those molecular hydrogen that are necessary for cooling and collapse of gas and dust to form the stars. So here we see like the incredible impact of the dust on cooling the whole environment and made one of the most important factors for the star formation to happen. And these videos, the credit of these videos of from University of California. So we can just like check their YouTube website. There's so many other cool stuff. It's been shown there. So, but actually, dust has also like another interesting role to play, which means actually they help those atomic hydrogen to come together and form the molecule hydrogen. How? I was listening to a podcast named like the Cosmic Savannah, and they use an analogy that dust actually like a dating app for for the atomic hydrogen, and then to help them to meet each other and form the molecule hydrogen. How? Like this is like the dust grains. If you imagine, we have like a solid grain, and once they meet an atomic hydrogen, let's assume we have a very boring neutral atomic hydrogen sitting in an interstellar medium, literally not doing very much. So the dust grains come here, and once they meet an atomic hydrogen, if it depends on like the some other factors of the dust as well, like some properties of dust. So these atomic hydrogen, like the neutral hydrogen atom, stick to that dust and sitting on the surface. And these grains just like migrate through the interstellar medium and meet another neutral atomic hydrogen sitting in another place in the interstellar medium, and the other one also stick to that dust. So, and then once like these two atomic hydrogen actually meet each other at the surface of the dust grain, and the dust grains are actually help them to meet each other and stay together to create the molecule hydrogen. Why we need a molecule hydrogen? Because without a molecule hydrogen, we cannot form the stars, because stars actually defined as the core collapse, and then the hydrogen fusion starts at the core. So we need molecule hydrogen to start burning at the core of the stars, and at the end, and then to create a heavier materials like carbon, magnesium, nickel and iron. So that's how the dust grains. It's actually literally can like be a dating app for two atomic hydrogen to be a molecule hydrogen. So so here, what is happening? Look, this is a very nice video from University of California that actually shows these kind of like environments. If they're cool enough, they come together, stay together, and then as they collapse under the gravity, they form a very, very, very dense core. And once the hydrogen burning starts to happen, we have the star. Actually, the definition of this star is like that. And the other leftover materials create a disk around that stars, which is the nursery of the planet. So for having a planet, for having the stars, we need dust. But where those dust comes from, like where are they created, and how did they create it? So we have like so as we mentioned, the stars. So here's this, if it's a star. So as I said, for creating a bigger and more complicated composition in solid grains, we need cool environment, like not to be hot. So if you imagine, like if this is our star, if this is for example like a red giant or like a big star, actually, because stars are different in their size and mass. So if you have like a big star like red giant, in the atmosphere of the red giant, it's big enough that the atmosphere of that star is far away enough to be cooler, to be much cooler rather than at the core of the stars. So these are the area that those heavier materials like carbon, magnesium, or other materials that already been created out of the nuclear fusions, they're cool enough to that these particles can come together, stick to each other, and form those solid grains, which we know as dust. And once like the stars finish its lifetime, and burning all the hydrogen that it's already been there, then for example, for the we have like the supernovae. And supernovae, what happens? I mean, that star, it just like exploded out and then deposit all those solid grains and dust grains that already created in the atmosphere of the stars. Then they deposit all those chemicals into this interstellar medium. So, and that is kind of like this the loop that happens over and over and over again. So these kind of chemicals be deposited into interstellar medium, then they create the molecular cloud, and like the same story happens as I already discuss about it. So we have different type of stars for sure. Depends on their mass, their size, their luminosity and temperature. But like kind of like the if this is a red supergiant, it becomes supernovae and then explode all those material. If this is a red giant, it's going to be a planetary nebula. Actually, like the name, it's nothing to do with a planet. It just because it seemed like a planet back in time, people named it planetary nebula. So what it does is actually like expand and like deposit the outer shell into the interstellar medium. So within like the at the later stage of like the star, the evolution of the lifetime of the stars, a kind of explosion happened that eject all those materials and dust grains back into the interstellar medium. But more, that is very interesting that star formation, it's a very, very inefficient process in the universe. Why? Because as you see, there's not that much dust compared to the other materials rather than the gas. So, and then the interstellar medium and then the environment needs to be cooled down. And within all those factors and criteria, it makes the star formation a very, very inefficient process. To just like give you a sense, like for example, for our Milky Way, the whole Milky Way with the amount like out of all the amount of like the materials which exist within the Milky Way, it just produced two two solar masses per year, which means like two stars like our own sign per year, which is incredibly low. So that's like the story for the and that's what I wanted to tell you for the dust grains and the revolution. My own research actually is in the Orion Nebulae. So if you had a chance to see like the Orion constellation at the winter time, it was a great. It's a very very nice clear constellation that you can pick it out, which is in Ojibwe culture, the indigenous culture. They call it the winter maker, which means like once you see the Orion constellation, it's winter time. So my project was like in the Orion molecule cloud sitting at the belt of like the Orion constellation, and I'm just like looking at the core scale, which I told you, which is around 10 to 4 times of the distance between Earth to Sun, and measure the size of the dust grains within the core in the Orion molecule cloud. And so many cool things happening. And then the size of the dust is very important for us because we actually should know at different stages dust grains have like the dust grains have like different size and different scales. Yeah, and I'm looking forward to expand these field of research in my PhD at Queen's because we have a lot of expert at Queen's uh, working a lot of expert at Queen's and star formation studies, and I'm so interested. So I'm done with the first half of my talk. So I'm like, keep your question. We're gonna get back to you so you can ask as many questions as you want. But before that, I want to move on to the second part of my talk, which is some fun things to do with your camera. So here it is. Actually, I just started my journey in astrophotography, and I enjoyed that a lot. And I had the opportunity to be a Clarny or like travel kind of like to some dark spot places to capture cool things. So I'm happy to share that with you. So first of all, I just wanted to inform you that once you see like a picture and like a picture of the Milky Way on Instagram or like in social media, there's like so many beautiful images with like so many interesting colors, and you might ask yourself that, are these color visible to the naked eye? Well, the answer is these color are real and have like a physical reason behind that because of different type of the stars. They have different colors, but the answer is that no, you do not see these kind of like picture with your naked eye at the dark sky. Because, and I'm just like inform you that if you just like go to stargazing, do not be disappointed to do not see that purple, blue, or all those kind of fancy colors in the sky. But what actually you see is something like that. It's just like a kind of like a dense horizontal cloud, like a path of the horizontal cloud, like pop up at the summer is like a good time for seeing that, and it's warm enough. So, but like it's a kind of like the cloudy horizontal path at the sky, so that is Milky Way if you see that. So, and it depends on your camera, you can just like capture them like more you can capture more details or not, but that is actually what you can see. I mean, for sure you can see way better than I did with my camera with your naked eye, but your eyes is not sensitive to those physical colors. So but I'm just like giving you some very common ranges, and then in the astrophotography, they're famous by knowing the golden numbers. So, and these are this. So first of all, if you have a digital camera and DSLR camera, any type, it doesn't matter. You just put it in a manual setting, and there's like three options you can control. So one of them is like exposure time. The second one is ISO, like and the ISO and like the sensitivity to light, and the third point is like the focal point. The it's the exposure time should be around 20 seconds, ISO around 3200, and focal point is about 2.8. But there's a common range that you can play with to go like 10 to 30 second, ISO between 1600 to 6400, and focal point between 2 to 4. But before just like play around with these numbers, what you should do is that first of all, find a very bright star, which I do not usually do like the astrophotography at winter time because it's cold. But like in the summer, you can point out to Arcturus or Vega. They're so bright, so you can just like uh, detect, kind of like see those stars at your eyepiece of your camera, and then zoom it out, and then make it very pointy, like just like a little bit play around with your focus, and then make that star as pointy as you can, and then just like zoom out, and then play with these range of like the numbers, and then you definitely capture the Milky Way, which is so interesting. But be careful that you do not go to the stargazing at the night which the moon is up, because moon is such a luminous object at the sky, so it's literally like that a lamp is on the dark sky, on the sky. So just avoid the moon, but as long as the moon is not there to illuminate the dark sky, you should be fine to capture the Milky Way. And then check the Milky Way, that like how up it is, like your horizon, to not be along with your horizon, so you definitely can see it at the sky. So depends on like the different lens. So with all kinds of like lens you have, you can capture the Milky Way. But depends on the lens you have, it might be noisy or not. So mine was like this little one, and I just like, this is a lens of my friend, so it was like very nice of her that I could borrow at Killarney Park to do some photography. But with both of the lens, like that previous picture that I showed you, that the actual color of the Milky Way that you could see with your eyes, I took it with a small lens. But with the big lens, you just have less noisy the picture. But if you know Photoshop enough, and then you're going to be expert on that, you can do image processing after, so that's not going to be an issue. And you can play around and then create a very high quality image. So, and then the second one that I just started to practice with is a star trail. A star trail is a very, very interesting thing that you can capture. Is that if you just like point your camera along with the Polaris and Northern Star, because it is along with the axis of the Earth, and Earth is around its own axis. So you can actually capture the trail of star, because the sky is a lot rise and set, rise and set. So if you just like have 48 picture or like less, and each like 30 exposure time, like each of your picture, then the way you do that is just you stack all your picture together, and then results it's give you a very nice star trail. So, and I'm just like introducing you very, very user-friendly software, which is compatible with either Mac, Windows, and Linux. So you can download it, and it's free. So what you do is just like there's an option at top left or top right, whatever. You just upload your pictures. For example, you have within those ranges that I already told you, the only thing you need to just like make sure that the Polaris is in your frame. So once you do that, you take like the pictures, 48 pictures around an hour. Around an hour is going to be 120 something, but at least you need a 40, 50 pictures of 30-second exposure time each. So once you have like all those pictures, you upload all those pictures, and then press the button of like stack them together, and then it just gives you a PNG or JPG file that you can do and start your Photoshop and image processing after. So, and I'm so glad that I can share you some cool pictures that I took from Florida Park. Which is a very, very nice area to visit, and it has like one of the darkest night that I've ever seen in my whole life. So it was very amazing. And these are like some pictures. Like this is one of the dome that we had at Clarny. So that is like the Milky Way, which was interesting because once you capture the Milky Way, you can see those amazing colors, which is actually real. Like this picture is like barely been edited, so it's purely what Milky Way looks like. And these colors are like physical, but your eyes are not necessarily sensitive to all of them. So I just like shoot out like a laser, which is just like interesting, and I just got a shooting star, which I was lucky that night was like full of the shooting star. And this is from the dome, and again you see like the shooting star at the top right, which was an amazing opportunity to be at. So here I just wanted to actually like use this opportunity to thank to one of my great mentor and teacher, Surush Kazemi, that I started my astrophotography journey with him. And he's in Iran right now, and he's a great, great astrophotographer. If you want, you can check out his Instagram under the Surush Kazemi underline. So, and that was like the picture that I was there once while he was like doing that. But yeah, and that was I think all for tonight. And thank you for your attention.
Well, thank you very, very much, Parisa. It's been wonderful hearing all of your great stories about dust and stargazing, and the images you showed us were indeed very inspiring. I just have to tip my York University hat to you as well
Thank
for
you.
your work as astronomer in residence. And just as a little note to any astronomers watching, if you too are interested in dark skies and, of course, astrophotography and giving tours, the Astronomer in Residence program is running again this summer. We can't promise you more Parisa out there, but just as a little side note to anyone watching who might be interested, it is running again this year. and the applications are open over on the YARQ site. So I think we've got a lot of questions for you. I'm not sure how many we're going to be able to get to or in what order. Emma, I'm going to go ahead and pass to you for any questions from YouTube.
Great. So the first question comes in from Zappan, who wants to know
Emma's
what.
Muted.
Oh, can you not hear me? Can you hear me?
So I think we're just having a small audio issue. I can hear Emma.
I cannot. Sorry.
We'll just pass over to our director.
Yeah, these kind of things always happen. I mean, not a big deal.
I don't have the list of questions. Sorry.
How about now? Anything?
I can hear Emma. I'm not sure what's going on YouTube. Shall we go to a break, folks, or do we need to
Yeah.
All right. Okie dokie.
Okay. So the first question is, what other chemical reactions happen on the surface of dust grains?
What other chemical reactions happen on the surface of dust grains?
Sorry, can you repeat that question again?
Yeah, what other chemical reactions can happen on the surface of dust grains?
Well, actually, as to my understanding, like one of the main responsibility of like the dust grains is just like they are sticky, depends on their metallicity. And the metallicity is like a little bit different in astronomy because astronomers call everything rather than hydrogen and helium as a metal, which is strange to chemists, but we call them as a metal. So depends on the level of like the metallicity, which means necessarily like the heavier material that those dust grains made of, like they're sticky. And like what it does, it just like stick like the different part of atoms and like that like help them to meet each other and then interact with each other. So on the dust grains, it's actually like the reaction between two different atoms, which I think chemists might like answer this better. That like, oh, I don't know if like different molecules meet each other, what can happen. But what I know as like the astronomer and like the physicist, that like this is a kind of the surface, and then they create platform, the different kind of like atoms can meet each other. So what is happening in that region, if like a very specific type of atom and another specific type of atom, that's the thing that I cannot like answer, I think, for now. But I think this is a kind of like more a platform for atoms to or molecules to meet each other and interact and collide.
Absolutely. That's a great question. So I'll go ahead and maybe take over from Emma for the questions, just to make sure that we're doing them in one way or another. But we do have another question about your photography, actually. So have you photographed a Starlink train?
Um, well, that's a very good question, but unfortunately not. I wish that I will be able to do it one day, but for now, I was just uh, like trying to capture Milky Way and star trail techniques, because star trails can be like very broad in its own sense. And also, I did a little bit like the still photography, but for that you need like a specific type of like the telescope with a filter. So what you do is just like you attach your camera with the lens of the telescope. But yeah, fortunately I will be able to capture it one day. But no.
Yes, indeed. I think we've all seen them at one time or another. One of our most common is it a UFO questions? No, it's just Starlink. Uh,
Yeah.
we do have a comment as well from CDB45 says excellent presentation. So just passing that on to you. So
Thank
people
you
are
so
very happy. And from Emma, we have a question: do your studies ever influence your astrophotography targets?
Well, yes, actually, because I was also like interested in the in comets. So I captured like the comets, I think one time, but like I am actually like very interesting by the tail of the comets, because when they just like pass like nearby the sun, like that kind of like the dust grains and all the things burn, and then that created lights. So like that tail of the comets has come from like the dust at some point. So comets are my favorite, but like I mean, I should be lucky to capture one or two in my lifetime, hopefully. So I just like two of them, but I missed the recent one. But yeah, I mean, yeah, everything. I'm dusty, but not dusty as in the earth wise, but just like space dust.
Excellent. Well, we have one more question, looks like, and actually one more comment as well. Another person, Adrienne, says, "Great presentation, well done." Um, and
Thank
then we
you.
have, okay, maybe two more questions from Peter. Can you describe how dust grains in space differ from dust grains that we see in everyday life? And as part of the same question, are any dust grains that we are familiar with similar to dust grains in space? I think you talked about this a little bit
Yeah.
already, but it's
Yeah, of course. Well, actually, the dust grains that we know on Earth is just like a bit different. For example, like I don't know, like if your hairs fall off, it can just like be like a dust, or they're like more complicated in their composition, because a lot of things can be like the dust, and they're bigger actually. And what we know as like the interplanetary dust, which is like actually those dust who actually made the planets made of. But the dust that we have in the space are more pure in their chemical composition. So as I mentioned, they're either be carbon rich or silicate rich. And then the silicate rich is, as you know, as what you know as a sand on Earth. So like literally like the sands that you go to the beach and touch it is the silicate. So it's the same kind of composition as we see in the space dust, but like the size of the space dust are micrometer. So you can see like the dust on Earth, right? So that would be like way bigger. And I just wanted to like mention that like a funny story that I had. I was just like talking to one of the other physicists, and they got back to me and just like, I really hate dust, and I was just like, because it's so bad for our detectors. But I was just like, okay, I truly understand you, and I think that's true. But the dust that I study is like way different, so they're not threat for your detectors and the lens. So yeah, they're different by their composition and their size.
well, I'm glad to know that I can't blame your dust for my dirty telescope mirror.
Yeah.
So I will definitely make sure that I don't do that in the future. I think we have time for one last quick question. So this is the
Yeah,
last
of
one from
course.
today. There might be other questions out there on YouTube, but this is the last one for our session. From Bill, what is your favorite planet besides Earth?
Well, if I will say Saturn because of this beautiful ring, that's okay, one of the most beautiful. But I really like Jupiter, like because it's specific on its own, and like my undergrad studies was like about Jupiter. But like I really like the pattern and the Jupiter, and like the way that like the way it is sitting there and its role in the kind of solar system, that it kind of like it's protect us from being attacked of so many other asteroids and comets because of like its gravity. So I would say Jupiter.
Wonderful. Thank you so much. And I think that's about the time for us to stop the question section officially. So thank you very, very much. I'm sure that we could, we're learning a lot about how dust is actually not bad. Is good, and of course
Yeah.
how to take fabulous, fabulous pictures. But we do have to move on to the last part of our show. So thank you once again, Parisa Nozari, MSc candidate at Queen's University, future PhD student, and of course, astronomer in residence extraordinaire.
Thank
Thank
you
you
so
very,
much.
very much.
Thank you for
And
having me.
it's been great having you on tonight. So with that, and with rounding off the evening tonight, I'd like to go ahead and change modes and pass over to and hand off to the president of Toronto Centre Rask, Tom Luton, to finish off the evening. Over to you, Tom.
All right. Well, thank you very much, Elena, and thank you very much to our wonderful speaker. So, good evening, everybody. Hope you're having a good time, and thank you very much for joining us this evening. So, let's just get on with the announcements. So, we've got two types of meetings. You've just been witness to one of our speaker nights, and then coming up in 2 weeks' time is going to be one of our recreational astronomy nights. If you're watching this live, and you like what you see and you'd like to come back in the future, please take that opportunity to say hello in the chat, enter some questions for the presenters. If you are a new member, please introduce yourself. And if you're coming to us from far outside the Toronto area, please let us know where you're coming from. So our next recreational astronomy night will be on Wednesday, the 5th of April, 7:30 p.m., both in person at the Ontario Science Centre and online as well. Arnold Brody will be discussing the sky this month. John Percy will be discussing the mysterious long secondary periods in red giants, explained or not. And we've still got one open slot available. Please contact Paul Markov if you'd like to present something. And then coming up at our speakers night in April, Dr. Haley Sapers will be talking about intraterrestrial to extraterrestrial, deep subsurface microbial communities and searching for life on Mars. That will be online only here on YouTube. Coming up at the DDO in the next few weeks, on Sunday, March the 26th at 12:30 p.m. online is Sunday Sun Gazing, followed by another session of Sunday sun gazing on Sunday, April the 9th, also 12:30 to 1 p.m. In all cases, you can register online. Links are to be found at our website, raskto.ca. On Saturday, April 29th at 9 p.m. Is our astronomy speakers night at the DDO in person. Dr. Keir Rogers will be talking about a search for dark matter in the cosmic web. And DDO Planetarium Day, 2 sessions on Sunday, April 30th, one from 1 p.m. to 2:30 p.m., and the second from 2:30 p.m. to 4 p.m. in person. Again, registration for all of these events can be found the links at raskto.ca. The CAO is still closed as the road is still covered in snow. We'll let you know as soon as things reopen. We're hoping sometime in April. We're looking for a new editor for our Scope Toronto Centre's publication. So if you like to edit and write, our Scope newsletter that we hopefully have is a bi-monthly publication that we send out to every Toronto Centre member. We are looking for a volunteer to act as our new editor. Please drop us a line at volunteer@raskto.ca or contact myself directly at president@raskto.ca. Also looking for a few other job postings. We're looking for an education and public outreach chair, a light pollution committee chair, a volunteer committee chair, and a marketing committee chair. Education and public outreach is always looking for additional members, especially those who can assist with online presentations and telescope camera operators for virtual star parties. Reminder that to volunteer, you first must be a member. Just contact myself at president@raskto.ca if you would like to help out. This is the part right to plug the joys of Rask membership. If you like what you've seen and if you'd like to take part and join us now that things are opening up again after COVID, you can renew or sign up online at secure.rask.ca. Gift memberships are also available from the national office. Contact the national office's membership secretary at mempub@rask.ca. And with that, I'd like to wish you all a very good night. Thank you very much for joining us. Please follow us on all the forms of social media that we've got listed here. If you like what you've seen here on YouTube, please like and subscribe and click the notification bell. Be safe. Keep looking up. Good night, everybody.